Let's do an example of a Newton's law problem where now we need to actually put in torques as well as forces. This goes back to doing what we did a long time ago with free body diagrams and looking at all the objects in a system and asking how they interact with one another through Newton's third law, as well as constructing Newton's second law, forces mass times acceleration, or torque equals I alpha for each of the objects individually. Let's imagine a mass little m is hanging off of a string from a pulley. The pulley itself is massive. It has a mass capital M and has a radius capital R, and the string is wound around the edge of the pulley. If the pulley is allowed to spin freely, of course, then the mass little m will start to pull downward because gravity pulls on little m, but it won't fall quite as fast as if there was no pulley there because, of course, the string is holding it back. Our goal will be to find the acceleration of this mass little m. We'll start by drawing free body diagrams for both the pulley and the mass little m separately. The pulley is just sitting out there at space. It won't fall in this case, but it will start to spin. And it will spin because there's a tension in a string that's pulling off at the edge of the pulley. There's a mass m out there as well, and we have to remember to draw its free body diagram. It wants to fall because of gravity. There's a force mg pointing straight down on it, and there's a tension T pulling straight back up at it. If there was no T, in other words, we cut the string, we know what would happen to that mass. It would fall with acceleration little g. But there is a string, and that's slowing it down. Now that we have those free body diagrams, those forces that are all there, we need to start looking at writing down Newton's second law wherever we can. So T is the tension of the string, and for the pulley, we start writing out there's only one torque. It's not going to be moving, so there's no F equals ma type equation. But it is going to be spinning, so there's a torque equals I alpha type equation. The torque in this case will equal R cross F, or T, tension in the string times capital R, the length of the pulley, and that has to equal I alpha. Now alpha, the angular acceleration of the pulley, is going to be related to the linear acceleration of the mass, because the more that the pulley rotates, the further down the mass little m will fall. This is an important point, since a theta rotation of the pulley represents a linear displacement down of the mass, and an acceleration, therefore an acceleration of the pulley represents an acceleration downward of the little mass. So for alpha, we're going to substitute a over r, where a is the acceleration of the mass, the little mass. And for I, we're going to insert our well-known formula for what's the moment of inertia of a disk, which is 1/2 capital mr squared. So this is about where we're at with the pulley. Now we move on. We're going to say this. We can eliminate some r's here. T equals ma over 2. For the little mass, we know that the sum of the forces has to equal mass times acceleration. This thing's moving. It's not spinning at all. The sum of the forces is mg minus t, and there's a minus sign there because t pulls in the opposite direction as g. And we're going to assume that a points downward. As a result, if we insert for t, we come up with mg is equal to little m plus capital M over 2 times a. Or in other words, a has to equal g times the ratio 2 times little m over 2 times little m plus capital M. That's our final answer. In other words, if capital M was really, really, really big, it was a massive pulley, then A would essentially be 0. It would get small, small, small. That's not so surprising. If you hang a ping pong ball, little m, off of a giant sphere or pulley, it's not going to start the pulley moving. On the other hand, if the mass of the pulley is very, very, very small, look what happens to the acceleration A of the mass, the hanging mass. It essentially becomes g, which is to say it's not really holding back the little mass, and it's almost going to go into free fall because it goes at acceleration g. That also makes sense. It's kind of like the same thing as if you cut the string. So the two extremes of this make sense to me, and so that's our final expression. That's A. That's the thing we try to find out. The really key point here is that we had to know that some objects are getting a torque, other objects are getting a sum of forces causing a linear acceleration. But there's a connection between the angular acceleration on one of these objects and the linear acceleration on the other. And that is through that key equation that A is r times alpha, or alpha is A over r. That just comes from the more the string unwinds off the pulley, the more the pulley rotates, and the more the mass can drop. They're linearly related. Theta is R times theta times R is S, or V equals R times omega, or A equals R times alpha. Those three equations are all very important to remember.